Okay, now we're getting to start about atomic physics. Now we're going to talk about all the physics that's happened since 1900. So some of the stuff that's going on. One of the things, and this actually started before 1900, is the argument over light. What is it a wave? Is it a particle? So our objectives are to explain the wave-particle duality of light, provide evidence that electromagnetic radiation has both a wave and a particle nature, and calculate the energy of a single photon and multiple photons. So, electromagnetic wave characteristics. Well, they have properties of both waves and particles. On the wave evidence side, you have refraction, which again is the bending of light as it enters a new medium, reflection, which is the bouncing of light off a barrier, interference, which is waves interfering with each other, the Doppler effect, which is a shift in frequency due to a moving source, diffraction, which is the bending around an obstacle in the same medium, and Young's double slit modulus, which is passing light through a double slit from a single source and getting it to interfere with itself. The particle evidence is blackbody radiation, Compton effect, and photoelectric effect, and we really haven't talked to those to a great amount of detail yet. That's one of the things we will be talking about. And particles of light energy are called photons. A photon is a packet of light energy. If you want to think about it that way, it's part of an energy wave. Sample: which phenomenon best provides evidence that light has a wave characteristics? Emission of light from an energy level transition. Well, that, to be honest with you, is more of a particle thing. B, diffraction of light through a single slit. Well, diffraction is definitely a wave particle, so a wave characteristic. So I would say that's our best answer. Let's look at the other two. Absorption of light. No, that could be a particle. Reflection off a mirror. Now that's a good one, because reflection is a wave property, but reflection is also a property that particles would have. If you think about bouncing a light wave off a mirror, okay, that's a wave. But if you think about bouncing a tennis ball off a mirror, it would also be a reflection. So you have to be careful with that one. B is the best answer. Now, the energy of a single photon, E is equal to HF. Very powerful equation. Remember, energy is the one thing that goes across every topic we talk about. E is equal to HF. Maybe in chemistry you said H nu and use nu for frequency. In physics we tend to use F for frequency. It's the same equation. H is called Planck's constant. And there's two common units that we use: 6.6 times 10 to the negative 34th joules times seconds, or 4.15 times 10 to the negative 15th electron volts times seconds. Now, which constant do you use? Well, that depends on what you're given in the equation. If you're given joules or something that will lead to joules, use the 6.6 number. If you're given electron volts, or if you're looking for maybe small amounts of energy, then maybe the electron volts one makes more sense. If they don't specify, you can give it in either one. What is the energy of a 101.1 megahertz photon used by an FM radio station? The 101.1 is what we call the call signal. It's the carrier wave. For an FM radio station, it's in the megahertz range. So 101.1 broadcasts on 101.1 megahertz. That's their carrier wave. On top of that, they superimpose the music, and the music gets to your stereo. So the frequency is 101.1 million hertz. That's all mega means. So a correct way to write it, to put it into our calculator, would be like this: 101.1 times 10 to the 6th hertz. Your calculator is still fine with that. Even though it's not correct formation, correct scientific notation, your calculator is still comfortable with that. E is equal to HF. Well, they didn't specify, so it doesn't really matter which H I use. I'm going to use 6.6 times 10 to the negative 34th joules times seconds times 101.1. There's a righto, not a typo, times 10 to the 6th hertz. And a hertz is a wave per second. Since you have seconds over seconds, they cancel out. 6.7 times 10 to the negative 25th joules. Now you could say joules times waves if you want, but we generally just drop the waves. The seconds have canceled out. Now, here's a shortcut you can take that will save you some time. We know that E is equal to HF. Well, we also know that all electromagnetic light and light energy type things travel at c, and c is equal to F times lambda. So if I solve that for F, I get F is equal to c over lambda. If I plug that into the other equation, I get E is equal to hc over lambda. Now, where this equation will help you is if they give you the wavelength. You can now do it in one step. If they gave you the wavelength previously, you could do it in two steps. You could use C equals F lambda, then use E equals HF. This allows you to do it in one step, which may save time. HC is a constant times a constant, so HC is not going to change. So this becomes a very useful equation if they give you the wavelength. The E is equal to HF is a better equation if they give you the frequency. It just saves you a step. Now, HC are known values, 1.99 times 10 to the negative 25th joules times meters, or 1240 electron volts times nanometers. Now, the 1240 electron volts times nanometers becomes a very useful constant because the the wavelengths of light for visible light are in the nanometer range. A nano is 10 to the negative 9th. So 400 nanometers to 700 nanometers are the standard frequencies of visible light. Red, orange, yellow, green, blue, indigo, violet. And of course red would be the longest, so red would be the 400 nanometers. So what is the energy of a 700 nanometer light wave? Well, the 700 nanometers, what they're giving me is the wavelength. So now it makes sense to use this equation. E is equal to hc over lambda. The hc in this case would be the nanometer hc, simply because your wavelength is in nanometers. So you don't have to do any fancy calculations and changings. 1240 electron volts times nanometers divided by 700 nanometers means 1.77 electron volts. Remember, electron volts are tiny, but here we're talking about a single photon, so we're talking about a tiny amount of energy. So now the next question is, what is the energy of a 700 nanometer photon in joules? Well, you can go back and convert everything and change it, but we already know what the energy is in electron volts, 1.77 electron volts. Why don't we just convert it to joules? If I have electron volts on the top, I'm going to need to put electron volts on the bottom to cancel them out. I'm going to want joules on the top. That's a number we know. 1.6 times 10 to the negative 19th joules is equal to 1 electron volt. Electron volts cancel out. I'm left with 2.8 times 10 to the negative 19th joules. Key thing to remember, electron volts are tiny. We're talking about the amount of energy required to move a single electron through a potential difference of 1 volt. So we're not talking about big numbers. Joules are relatively big compared to electron volts. Now, for multiple photons, the E is equal to HF or HC over lambda is the energy of a single photon. Well, the total energy would have to be multiples of that. So HF is the energy of a single photon. N is an integer that equals the number of photons. So if I have the total amount of energy, I can divide by the energy of a single photon, and I can get how many photons. This is useful if I want to figure out the total energy emitted by a light bulb, by the sun, by anything like that. Hope that helped.